Okay, so this is item 4.6 on page 91, and let me go ahead and read this item for you. So the idea here is to show you how to do a 5-point summary. It says seizures following bacterial meningitis. In exercise 4.4, you calculate the mean, median of induction times in 13 seizure cases. Data were, it gives you these data, and I have them all listed there. So you can take a look at those. So this is the same as is in your textbook. So if you can't see these very well, just go to your textbook and you will be able to see them. Now construct a box plot for these data. Are there any outside values in this data set? Does the box plot show any evidence of asymmetry? Okay, so, well, this to create a box plot, we need several values. 5 values, in fact, what's called a 5-point summary. 5-point summary includes the minimum, the maximum, the median, the value for quartile 1, and the value for quartile 3. So that's 5 different points. So we're going to start by calculating the median here. So the median is the value smack right in the middle. We have 13 values here, so because we have an odd number, we actually have an easy way of identifying the median. But if you didn't have an odd number, you still would have to figure it out. So what you do is you take the number of values, which is 13, you add 1 to that, so it gives us 14, and divide by 2 gives us 7. So this is where the median is located. It's the 7th value in this ordered array from smallest to largest. 1, 2, 3, 4, 5, 6, 7. The value is 7. The value is 24. The value is 24 in this ordered array. All right, so that's our first value that we calculated was the mean. Second, we need to find the mean of the lower half and the mean of the upper half. Because we have an odd number of values, we include the median, the actual median for the entire 13 values in the lower half and in the upper half. So for the lower half, to calculate the first quartile, we're going to have 1, 2, 3, 4, 5, 6, plus 1 is 7 values. For the upper half, we're going to have 1, 2, 3, 4, 5, 6, plus 1 is 7 values, because we're including the median in both the lower half and the upper half. Okay? So we do the same in calculating the median of the lower half. The median of the lower half is 7, because we have 7 values there now, plus 1 equals 8 divided by 2 is 4. So it's the 4th value in this array. 1, 2, 3, 4. And the value there is itself 4. So now we need to calculate the median of the upper half, starting with 24, right? Because that's, remember, the median of all 13 values is included in both halves when we have an odd number of values. So 1, 2, 3, 4, 5, 6, 7. And the median here is, again, it's the 4th value, 1, 2, 3, 4. That's 36. So your median for the upper half is 36. We know our minimum value in this ordered array is 0.1. Our maximum value is 96. So our 5-point summary will be 0.10, 4, which is the median of the lower half, 24, which is the median of the entire array of values, 13 values, 36, which is the median of the upper half, and 96. So these values are actually the minimum, quartile 1, the median, quartile 3, the maximum. All right, so that calculates the 5-point summary. Next thing we need is the interquartile range. The interquartile range is Q3 minus Q1. So it's basically the middle 50% of the distribution. So it's the quartile 1 represents the lower 25% of the population, of the sample, excuse me. Quartile, the median is the middle point, so below the median you have 50%, above the median you have 50%. The third quartile represents the 75% of the sample. So below the third quartile, you have 75% of the sample. Above it, you have 25%. So if we take quartile 3 minus quartile 1, we get 36 minus 4, we get 32. So our interquartile range would be 32. Now, in calculating and in drawing this figure, now a lot of people just use the interquartile range as a measure of variability, so that's fine. Some people use the range, which is the highest versus the lowest value, 96 minus 0.10. You can use that as well, but it's not very instructive because of the too much weight is being given to the outside values. In drawing this box whisker plot, we need these 2 points here, one here and one here, right? The endpoints for these whiskers. To calculate these are called fences, right? Well, actually, we use the fences in order to find these values. So the lower fence of our box plot would be quartile 1, whatever our quartile 1 is, which is 4, right? Minus 1.5 or 1.5 times the interquartile range. So in our case, 4 is quartile 1. We multiply 1.5 times our interquartile range, which we calculated as 32. So that's 4 minus 48 is negative 44. Now we're going to draw this line, right? We're going for the what we call the lower inside value, the value that's closest to the lower fence. So our lower fence is minus 44. Well, there are no negative values here. Our smallest value is 0.10. So the closest value in this array to minus 44 is 0.10. So we're going to draw a line right here at 0.10. We're going to do the same for the upper part of this distribution. And here we're going to make what's called an upper fence. So in this case, the upper fence is quartile 3 plus 1.5 times the interquartile range. Quartile 3 value is 36 plus 1.5 times 32, so that's 36 plus 48, gives us 84. And the closest value inside of 84, is 55, right? So our what we call our upper inside value is 55. Just like our lower inside value was 0.10, our upper inside value is 55. Now, we had no value smaller than 0.10, so there are no outliers on this side, on the lower side of the distribution, but there is an outlier, 96, that's on the outside of our upper inside value. That's 96. So we have at least one outlier here. So you can see that this distribution, while 50% of the sample is right in here, between 4 and 36, we do have at least one outlier. So that would actually this is probably a very influential case. What we'd have to do is study to see if that's our true value, or if it's not a true value, then we have to make a decision if we were doing the study whether we want to keep that or not. Given that there's only 13 values, it would be really hard for me to want to reject any one value. So that's how you do a box plot. So you might be prepared to do one of those. Let's move to the next item, 4.10 on page 95. So here we have, so this is page 95. It says 4.10. Heart rate. An individual with an irregular heartbeat is given a medication to stabilize his condition. Heart rate beats per minute before and after treatment are shown here. Okay, those are the values. Determine the means and standard deviations before and after treatment. The question is, did the drug work? Well, we can't answer that actually, technically, unless we do a statistical test. So we're just going to calculate the means and the standard deviations here. So it's not important that we order our array here because we're not calculating a median. But we have 1, 2, 3, 4, 5, 6 values. Let X sub B stand for heart rate before and x sub a equals heart rate after the treatment. N sub b is the sample size of the before, and n sub a is the sample size after the treatment. It's the same individual, so we have 6 individuals in both cases. The mean of x sub b, I'm going to put a little bar over here. As I said, these are Latin letters. Mean of x is mean x sub b. We're just going to summate starting from the first value, which is 65, all the way to the last value, which is 60, across all 6 values. We're going to summate all the values and divide by the sample size. So we get 420 divided by 6 equals 70. For after, the mean is exactly the same. So you think, okay, well maybe this isn't working. But it's going to be that's an interesting look. But so later on we'll be able to make all kinds of interesting calculations. But it doesn't look like much is changing from this treatment. So we have to calculate the variance for each of these. There's 2 different formulas for the variance. There's the formula that I showed you in class, the non-shortcut formula, which is the summation of the difference. So this is called the sum of squared, because we're squaring it, sum of squared differences between each individual value and its mean, divided by n minus 1, because we lose a degree of freedom since we're estimating the population value from the sample. Now, I'm going to show you how I calculated the shortcut formula. Just quickly, if you want to ignore this part, you can, but I wouldn't, because it just helps you review certain types of calculations. So we have a square or power of 2. That means we're multiplying this value times itself. So I break this into those 2 components of the product, those 2 terms, right? So x b sub I minus its mean, and again here, and then dividing by n sub b minus 1. If I work this out, I'd be multiplying x sub b, and I notice I have an I here for individual, but I want to keep the b so you know it's before. So I'd multiply these times themselves, so that's where we got the x sub bi squared. I multiply negative mean times this value here, so I get this term right here, and I do it again, right? I do it a second time when I go here and here, so I get it again. Now, one case I have the mean behind, one case I have the mean ahead. That doesn't really make any difference. It's the same product. And then finally I multiply these 2 means together and I get mean squared. And then we're dividing it by this, n sub b minus 1. Let's focus on the numerator only, because in the end we're still going to have to divide the whole term by this. So these 2 terms can be added together because they are exactly the same. Despite them looking different right here, they're exactly the same. So we ended up simplifying this term, right? This x squared basically minus 2 xbi times its mean, and then we add it to the mean again. Now let's distribute the summation across here. So we get the sum of x sub bi squared. Now 2 is a constant, as is the mean. These are both constants. So we can always pull a constant out of a summation sign, because we're only going to be summing the x sub bi. So here we pulled the 2 out, and we're still going to have to pull this mean out. The mean is a constant. It's one single value, and it'll be the same here. So let's simplify that term some more. So this stays the same, right? X sub b sub I squared. So we pulled out both the 2 and the mean, because they're both constants, multiplied by x sub bi. Now here we're basically summating a constant, and we're doing it n different times, right? We're doing it n different times. All right, so we're going to sum, basically what we're doing is we're summing from I to n 1, because we're going to do this n different times, right? It's a constant, we're just going to add it n different times. Basically we're going to add it 6 different times. So just for simplification here, I have the mean, I pull it out, the constant, times the sum of 1, which ends up being, as you can see here, n times the mean squared, right? We pull out mean squared here. Everything else stays the same. Here, we are going to use this, we're going to do something with this mean. The mean is the same as we know from calculating the mean, summation of all values divided by n, right? This value stays the same, and we're doing the same here, summation of all the x values divided by n, and we're squaring it, multiplying it by n. So we're doing all these things because we're going to continue to simplify it. And again, if you're not interested in the math part here, that's fine, but it's going to help. The review of this math is going to actually help you in the long run to understand what we're doing. Okay, so we can simplify some more here. All right, so we have xb sub I squared, so the summation there. We have 2 times this sum, because you can multiply these two terms together and square them. That's what we have up here, divided by n. Here we're going to square each, the numerator and the denominator, so we're going to have x sub bi squared and n squared. And then we have an n out here, right? I just moved it to the other side. And that'll cancel out one of the n's. So what we have left over then is this formula right here. Now we have 2 of these, which is the same as this. There's only one of them, and this is a negative, so we're going to eliminate one of them, right? Negative 2 times this value plus one of these values would equal negative one of those values, which is what we end up having here, right? So we only have one left. So we have this summation of x sub bi squared minus summation of x sub bi, the whole thing squared, divided by n. Why is this a shortcut formula? Well, it's a shortcut formula because it allows us to summarize the values better and then use something like Excel to fill in the blanks. And that's exactly what we're going to do in the next and last slide here. So here's this variance rewritten, formula for the variance rewritten. So this is what we just did now. And now we just need the summation of x sub bi squared. We need these values here, summation of x sub bi, and then we're going to square them and divide by n. So let's set up these data in Excel, which is what I did here. Alright, so based on that formula, we need the summation of all of the x sub bi squared. So here's our values are 60 beforehand. They're 65, 85, 90, 65, 55, and 60, and then this is what they are after. If we square each of those terms, right, we'll get 65 squared, which is, well, I'm going to do that for you just so you can remember how I did this. So we need to square this term. So we're going to hit the function key, and I used this several times, so I found the power function, which would be in math, under math and trig. And the number I want to square is 65, and the power is 2, because we're raising it to the second power. That would give us this value, and I need to do it for each of the individual values, so I'm just going to scroll down like this. Okay, so this would give us the squares of each of these values, right? And for after, let's see if this would work. So we know this is for cell B28, which is right here. So I need to square for after. I need cell C28, right? Okay, so it's B28. So we need to do C28. Let's see if this will work. So if I pull this over here, it gives me the square of cell C28. Perfect. So that's a 68 squared is 4624. I drag this down here and I get all the squares. So let's go back to our formula. What do we need? We need the sum of all the xbi squared. Alright, let's summate this. Oops. Summate this. We need a sum of this and then square it. Okay. Well, here is the sum, right? So we need the sum of all those squares, right? So we need to summate this value right here. So let's go ahead and do that. Let's summate this. So by hitting auto sum, it'll sum all these values above me. Now you just double check to make sure those are the ones you want and hit enter. And then I need the sum of these values as well, so I can drag this over, and this is going to sum. Let me double check. E28 to E33, there's E28 to E33. Alright, so I got that. So I need the sum of squares. What else do I need? Let's see. I need the sum of the xbi squared. That's different, okay? It's not the sum of squares. This is the square of the sum of all these values. So I need to square this thingy right here. Sum squared. So I need to hit f of x power. The number I want is this one, and I need to square it. Hit OK. There you go. I did that. I need the same for the other one. Yeah, well, they're obviously the same. Uh-oh. Not good, right? So let's go ahead and calculate the formula for... Let's go ahead and calculate the variance. Let's see what we need to do in order to calculate the variance. Okay, we need the summation of all the xbi squared minus the summation of xbi squared divided by n. Alright, let's see if I tried to set this up earlier, but it doesn't look right here. Okay, so we got E35. Oh, okay, I did it this way before. I need the sum of squares. Did I do the sum of squares? Let's see. Oh, I did it right here. Okay. So, sum of squares. So it's 3040. So this is in cell D34. D34, okay. What else do I need? So I need that. I need the square, take the sum of all the values and square them. Let's see, do I have that? The sum of all the values and square them is actually right here. So let's go divided by this, okay, and that's divided by n, right? If you look at this, it's divided by n right here. Okay, so and n is 6, so that's divided by 6. I got that, and then the whole thing's divided by n minus 1. So this should be what we need, and it's 200. All right. So this says that the variance is 200. Well, let's check that by calculating the variance of these values here. So we're going to go to f sub x, and I need the variance, which you can find under statistics, and I want the variance of these values here, and I hit enter, and I get 200. So I did the right thing. Now for the last things, I need the standard deviation. The standard deviation is the square root of the variance. So I'm just going to do the square root. So I need a square root, so I'm going to go look under math and trig, find square root, hit OK. What number do I want the square root? I want the square root of 200. Hit enter, and it's 14.14214. Okay, so that was pretty simple. So that's how you calculate this value. How you calculate a variance. So if we want to do it for the next value, we want to do for after to see if there's a difference. We have variance of 200 for the before, one variance for after. So we're going to do basically the same thing. So our formula here was I'm just going to move this down here, and I'm going to redo this. I'm just using these. I just use this to replicate the formula here, but now I have to fill in the correct values. So we start with the sum of the squares, right? The sum of the squares, which is, in this case, for after, it's 29410, and this is in cell E34. So let's move that to E34. So I'm just doing this in a way that makes my life easier, and you should do the same for yourselves, okay? Then this is the sum of the values squared, which is sum of the values and then square them. is right here. Everything else should be the same, right? Because you're dividing 6 and then 5. We get 2. So, oh, look at the variance. A lot more variability in the beginning, in the before and after. So I would think that even though you saw the means didn't change, I think people are better off afterwards. They're way, way better off. But let's go ahead and calculate this variance. Now, I should be able to drag this over and get the right value. Let me see. Yep, sure it is. Because look, this is the variance for C28 to C33 and C28 to C33. And take the square root of that value. I should be able to drag this over here. And it's 1.414. Alright, so what's the moral to this story here? You can use Excel to do all of your work, but you got to just make sure you check everything very well. Make sure that you have the right values in every case. And let's look at our results here. As you can see, we've got 200 for before and then 2 for after. Okay, and these are all correct as well. All of these means, standard deviations, variances are all correct. That's it. Okay, so I hope this helped a lot, but you need to review it. That's the only way you can do it. Just review it. All right, thank you. Bye.